said before. So now we'll try to do quickly to set up reverse Monte Carlo, and then if some time is left, maybe we can see another example of GNXAS. So if you go in the folder that you copied, there are various examples. So now if you go in the BR2 RMC, so this one, you will find the input files for the RMC programs. So again, as before, usually I create different folders for the various programs. So I will not talk maybe about Fagen because it's the same of GNXAS. So if you go into the folder init for initial, this is for creating the I don't know why it's empty. Wait. This is not empty. Sorry, I have some folders that are empty. Wait, let me check.
You said the init folder, there is some data here, I think, so there was a mistake, a little problem with the copying, I think. But I see.
Yeah, I will copy again.
Okay.
So okay, let me copy some other place. Okay. Sorry about that. I had to copy because before it was empty for some reason. Okay, now I can see the files. So so if you go into the folder init, this is for the initial configuration. And for the initial configuration, actually we use a program which is just called Cremol RMSC, which is basically an extension of the Cremol that we use with GNXAS. So the input file is the same. It has just an additional flag in the end that is used for creating the RMC configuration, initial configuration. So if we look at this, sorry, I went quick. This input file, so cremol br2rmc.in. If you open it, you see that is basically very similar to what we see before with the normal Kreml. Okay, in this case, the system we are treating is a different one. This is bromine molecules, so it's just 2 atoms at a given distance. And but the other is very similar, so it's KH. So here we have 1, and we use complex potential. Of course, we need to remember to change the energy of the KH, and yeah. So the different part is these 2 additional parameters in the end. So for molecules, this is the number of replicas. So how many molecules we want to have. Again, this is for molecules. These replicas are used to simulate thermal vibration by using an ensemble. So instead of having, we have many molecules, we average the signal over all molecules and we simulate thermal disorder. And the second parameter is just how to say, a Gaussian factor that we can give to give some initial distortion. But we can also leave 0 and start from the initial configuration that we give. So in this case, I suggest maybe we use less molecules because we will run on the cluster. So maybe 100 replicas is okay. Maybe it's sufficient statistically. So these 100 replicas and 2 atoms. So for each replica, so 200 atoms total. So it's quite a small simulation. Usually we need much more bigger system, but this simulation usually are run on a cluster and for many times. So now, just for an example, just to set up, we use a smaller cluster. Okay. Save and quit, and then we just run as before, Kreml RMC, and then left arrow and the name of the input file. Okay, this is done, and yeah, I think this is sorry, the name of the output. So in this case, the configuration file is this br2xyz.rmc, and we can look at it. Yeah. So if we look at it, there is let's say an header which contains information on the structure. So we have the name of the system. Then we have here XYZ, which means it's a molecular case. So the coordinates are in real space. Instead for what to say, for condensed system, we use the boundary condition, periodic boundary condition. Usually we use the fractional coordinates are written here instead. So we have 2 atoms per molecules, and for a total of 100 molecules, and we have only one type of atoms, only bromine atoms, and okay, disordered, an initial disordered configuration. And here this starts tell the RMC where to start. This is useful when you run many simulations. Then maybe you want to start from already equilibrated configuration, so you will use this start in a later file. And then we have a list of coordinates. It's just XYZ coordinates and then the type of atoms. Okay. So this is our initial configuration. Then what we need is the is the GNXAS files. So if we go into the GNXAS folder, so in this case we need again maybe to run Fagen, and the input file is created by Cremor RMC. Okay, in this case I will skip because we have seen Fagen before, and the input file is just created by Cremor, so you just need to run that. So we go instead inside the GNXAS folder, and here you see we have many files, and the input file is this brhsas.in, and again if we open this, so this is basically the same as GNXAS. So we want to calculate the two-body signal for many distances. This is because, as I said before, just to speed up the calculation, because it would be too slow to call GNXAS every time. Instead, we pre-calculate the signal for some distances, and then when we do the calculation, then we interpolate the phase shifts and the amplitude on the correct distance in the module. This is string for the output file. I will change this to BR2. This okay. In this case, it's not important. As I said before, this is modes how to calculate the derivatives and so on. So now this is the two-body signals that we want to calculate. So as you see here, we have 13 two-body signals, which are given by these columns. So it's not necessary that you do the space. I want to do just to make it more clear for you to understand, but it's not necessary. So if you see, we start from 2.1 and we go up to 2.9. So then the second column, if you remember, is the degeneracy. In this case, we want to calculate only for one type of atom, because then the degeneracy is already inside the RMC, because we have a given number of atoms. So and okay, in this case it's only two atom system, but even if you have more atoms, when you calculate the signal, you just calculate for degeneracy of 1, and then the last ones are just which phase shifts to use that I've written into these files. So 1 and 2 is just the phase shift of excited bromine and neutral bromine. So if you see here, so we calculate for all these distances, so we will have 13 files. Then, okay, free body and full body, we don't calculate anything. And then we need the same as before for GNXAS. We need to give the angular momentum of the excited for the electron, which for k edge is 0. Then these are just parameters for the graphical output, so we can leave as it is. So write, save, and then to run, we can just use GNXAS. calculate this. As usual, with the left arrow and the input file. Okay, and after some time it finishes, and we see here all the files that have been created. So as before, we have the files are written with the three letters that we choose. Then we have a G2 for indicating two body, and there are a number, successive number, that indicates the various signals. So in this case, we will have a total of 13, as I said, and so 1. So, and the 1 dot there is for total two body, and 0, 1, x2 and x4 instead are the multiple scattering ones. But in this case, we will use the total ones. So, okay. Once we have done this, what is left is the experimental data. We need to calculate the noise on the experimental data. So for that, if we go into the folder ._rmc, this one, so you see, yeah, there are various files. So the actual experimental data is this pro.dat. So we can plot it with a new plot. So in this case, for RMC, we don't use the raw experimental data, but we use the extracted GNXAS signal. So it takes some time, but basically we'll have the so-called the key of k as a function of k of the excited photoelectron wave vector. Yes, so in this case, this is our experimental signal, and you can see, especially at high k, there is some noise. So to calculate the noise, we have a small program called noise that is basically the same that is incorporated inside the video to estimate the noise. And basically what the program does is that it divides the experimental data in small intervals and feed it with some polynomial degree, then takes the difference and estimates that the difference is the noise. So to run that, you can just write noise on the terminal, and so without creating an input file, because it requires very few input file. So first it asks what is the name of the data file. So we write pro.dat. Then it asks if it's GNXAS signal or it's total absorption. So in this case, it's GNXAS. And then it's finished. So here you can see the various intervals within the points. You see it's very small intervals. And this is the noise estimation. Then it writes 3 different files. 2 are for output files that you can plot with top drawer. I will not do it because it's quite slow to load from here, but you can try on your PC to do td bro_noise.top, or also this bro noise.top. It will show you the estimated noise. And then it writes in this data file, this is what is used in the reverse Monte Carlo program as input. Okay. I think now we have all the components that we need. So we can go inside the folder RMC. So first of all, let's copy the initial configuration that we created before. So it was in the init folder. So this file we created before with Cremol RMC. Copied from that folder to here. Yes. So overwrite, it's not a problem. So if you make sure, if you look at the file with using the command boa, you should have only 100 replicas. That is the file that we created before. Okay. Then let's see the input file for the RMC program, which is this beer2rmc.in. So first one is just the name for the coordinates file. So coordinates file is this beer2 xyz.rmc that we just copied. Then this is just again 3 letters for the output files. I will call it B2R just to distinguish, or maybe wait, I can call it 100 so that I know it's 100 replicas. Then there are some parameters. So this is the maximum cutoff that we want to calculate, but yeah.
When you are mentioning about 100 replicas, I am just asking this to make sure that I understood it correctly. So this essentially means 100 configurations in each cycle. Did I understand it correctly?
Yeah. So just to be more clear, so if you look at this configuration file, so it means we have 100 replicas of the same molecule.
Yeah,
So
basically, 100 configurations or arrangement of molecule in the box that we are going to consider.
Yeah. But basically, in this case, we don't have a box. We just have various molecules that are disconnected from each other. So, for example,
so I was wondering. Sorry to interrupt. I was wondering.
Yeah. No, it's okay.
Is it somehow possible to visualize this one, like it's a graphical visualizer or something like this? So because
you say usually. So one problem is that if you visualize all these molecules, this will be very overlapped, because if you see here the coordinates. So, for example, this is one molecule, then this is the next molecules, and these two coordinates are quite similar, but in the program it's coded in a way that they are in different space, let's say, even if the coordinates is the same. So to visualize, usually, for molecules, maybe you can just visualize one molecules, and what I usually do is just copy the coordinates for and paste it in some other programs. I don't know, there are many programs, I don't know which you usually use,
example,
but
Vesta
for
or something like this.
I think Vesta or XCrisDance also I use. I think both of this program reads simple XYZ file, so I just copy the coordinates and create that XYZ file. And also for how to say, instead for how to say, when you have a box with the periodic boundary condition, in that case, all the boxes you can plot it. Yeah.
Okay, thanks. Thank you.
Okay. So, so this is the cutoff, which for molecules actually it's much higher, so it's not used, but it's useful when you have a box, because you can limit how far you will go from this let's say from the center of each atom to reduce calculation time. And then the next one instead is important, is the closest approach. So what is the minimum distance that the molecules can reach? So I think this one we should put 2.1, because when we calculated the x-axis we started from 2.1, so let's put 2.1. So basically, if one atom will move closer to another atom below this distance, then the move is always rejected. So it's like an art sphere potential. Then there is an additional flag here to put a maximum distance constraint, and I think for molecules this is better to use. So here we put yes, and then we have to put a maximum distance constraint that could be, for example, 2.9, because that is the maximum distance that we calculated the x-axis for. So this means the two atoms in the molecule will not move closer than 2.1 and will not move farther than 2.9. Because for molecules, sometimes can happen that basically the molecules disintegrate and you don't have your system anymore. Okay, then.
In this file, is there the limit of displacement? So that you were mentioning about some point.
Yeah. So it's basically how. So every time you move an atom, it calculates the distance with the other atoms, and if it's closer than this distance, or it's greater than this distance with some other atom, the move is rejected. So it will stay inside these limits. Next one is number of experimental data that we use. So only use one, and then we use this raw.dat that we have seen before. So this is okay. Then next one, if the data inside this file is in K or in energy, in electron volt, but as I showed before, it was in as a function of the photoelectron wave function. So we put 0. The weight of the on the input data. So this was how to say, the exocynia. Sometimes it's plotted as times k or times k square or times k3. This is that exponential on the k weight, and for this data it was 1. So here just put 1. Then this number is how to say, the photoexcited atom, photoexcited element, let's say. But it's defined by a number. In this case, we have only 2 bromine atoms, so it's bromium K edge, of course. But for example, if we have 2 different atoms, we have to specify which one is the photoexcited one, because the exocynia is calculated only starting from that photoexcited atom. Then this is the H0 parameter. Sorry, this is the energy edge. Sorry. So in this case, I don't know why it's 0, but okay, we can leave it 0. I will explain why later. Otherwise, you can put the experimental energy edge. Then here we put the noise on the experimental data. So if you remember, before we calculated, and it created this BRO.noise file. So we just put that noise as noise of the experimental file. Then next, this is for if you have radial distribution function models. So as I said, this program refines both EXAS and diffraction data, but in this case we will not use. So just leave 0. So there are no Baire distribution function models. Then this is just a flag for how to say, for the histogram, for when we calculate the Baire distribution function, how much sorry, the initial distance, so starting from 2.0, and the delta of the Baire distribution function. So because now we're using only 100 replicas, I suggest this be increased by 0.05, because 0.01 is probably too fine for such a low number of replicas. This is just another output parameters for graphical purposes. So just the weight on the output files, can just leave 1. Then this one is the number of RMC steps. So in our program, what we consider one step is when all atoms have been moved. So one step means all in our case 200 atoms, have been tried to move. So sometimes people instead consider the number of RMC moves the single moves of one atom. So again, just to save a bit of time, maybe we can do, I don't know, 300 steps. Yeah. Because otherwise maybe it takes too much time. Then this is the steps. How often do you want to update the visual output, and how often do you want to save the configuration? So this means if we use 150, that every step the output, the graphical output are updated, and the 50 means every 50 step a configuration is saved, and the configuration is saved in the same configuration file. It's appended at the end. So then here we need to say how many steps for equilibration. So this is because after this equilibration point, the program will calculate the average quantities, will average over all the configuration, while before that it will calculate only from the last one. So let's say 200, maybe even, I think 150 is okay. Yeah. Okay. So of course another way is just to run a given number of steps and then see for yourself and then restart another simulation. This is also another way. And this is the initial value of the delta parameter, so how much we will try to move our atoms. And I remember that this delta is changed during the simulation, so it will be adjusted by itself. So it's not, it's okay basically to put any value. Usually, yeah, 0.04, 0.05 is an okay initial value. This is how often do you want to change this delta parameter? So this will be checked at every step. This is the E0 parameter. So in this case, okay, we can leave 0. So and the reason before I put I left the energy edge as 0 is because actually in GNXAS what is important is the difference between this H0 and the energy edge. So in this case the difference is 0. So and it is okay. Okay, for BR2 the H0 is not actually far from the experimental energy edge, so we can leave just like this. And then the S0 square, this 0 square is basically 1, because of course it's a 2-atom molecule, so we don't have many body reduction. This is the experimental resolution. It's full width half maximum experimental resolution. This is actually the effect of the experimental resolution. Actually, many programs does not take into account because it's a very small effect at low energy. It's more important when the energy becomes very high. So, but anyway, it's for this case you can leave 2, and then we have to give the DER files calculated by GNXAS, and to do that first we need to say how many how many different type of signal we will give. So this is for when you have multi-atomic components to distinguish between different elements. So again, in this case, we have only one, so we just put one. But for example, like in the slide I show you, there was a silver bromide case. In that case, you have 3 different signal. You have one for actually in that case it was double edge, so you have 4 different signal, because you have silver for the silver KH and silver bromine for the silver KH, and then you have bromine for the bromine KH and the bromine silver for the bromine KH. So in general, if you have one edge and 2 elements, you will have 2 different signal, because like, let's say again, for example, if you have an iron nickel alloy and you are refining nickel KH, you will have a nickel iron signal and a nickel nickel signal, but you will not have iron signal for the nickel KH. In the case you put also the iron KH, then you have to add additional signal. Okay. In this case, we have only bromine signal, so only one signal, and the 2 atoms corresponding to the signals are 1 and 1. I will show later how to understand these numbers, and this is how many signals we have. So if you remember before, we calculated 13 different signals. And then you have to give only the name of the first one, and the program will automatically read all 13 ones. So if I remember, I called them BR2 and then G201 dot there. And if you remember, so this is the total 2 body. So in this case, we are not using the multiple scattering expansions one. Okay. Then last one is, let's say, a cutoff for GNXAS. This is used mostly for solid system to save time. As I said in my presentation, we calculate the signal only up to a cutoff, because after, let's say, 5 or 6 angstrom, the GNXAS signal becomes basically 0. So we use this cutoff. So in this case, instead we have molecules, we can change the cutoff up to the maximum. Okay. We can save this and quit. And so the first time you run the program and you read the coordinate files, this ref tab file will be created. And what this ref tab file tells you is basically the corresponding number for the type of atom. So okay, and for the pairs. So in this case, okay, we have only one atom, so this is 1, and for the pair we are only 1. But for example, if we have 2 atoms, we will have, for example, bromine, and the silver will be atom number 2. And then we will have the different pairs that are specified with different numbers. And these numbers for the pair are just for the output files. because let me show you. So I don't have here an example, but so if you see, one output that is created is this RAD RMC. So, and the RAD RMC contain the pair distribution function. So usually for one atom there is only the total distribution function, but if you have different atomic species, you have the total distribution function and you have the partial pair distribution function. And in that case, those partial distribution function will be called like 0, 1, 0, 2. And this number corresponds to the pairs that are written in the file that I showed you before, which is that this ref-tab file. It is inside this folder. It is called CHK, which stands for check, because can be used for checking the input files. So for example, other files is the phase shifts. This is mainly for debugging reason actually, but to check if there is some error somewhere, these are written. Okay. Then another important point is that when you run the program, it also creates this SHRMC, and this is basically a new plot script. So if we look at the content, it's basically a script for new plot to check this while the simulation is running, basically. And it is what I showed you before in the presentation. It's basically window similar to this. I don't think I will be able to show you from my laptop because it's quite slow to load from the cluster in Hungary, but maybe you can run it on your laptop, and you can run it simply by doing new plot input file SHRMC while it's running on or when it's ended. Okay, so with that said, we can run the program now. So the program of the RMC is called GNXAS. RMC GNXAS. And again, the input file. So left arrow and the name of the input file. So usually, let's say, when I run this on my workstation or my cluster, usually what I do is that then I save the output file into somewhere called like log, because it may take some time to finish, something like this, and also I can check the log later. But okay, for now I will just run in real time, and I will let the program write on the terminal. So hopefully should not take too much time, because it's only 300 steps, and you see it's running quite fast. Okay, and it's finished. So in this case, finished quite fast because again we only use 300 steps, and we had only 100 replicas of the molecule. But for example, if you use one example I show you in the presentation of liquid nickel, if you do liquid nickel with 2000 atoms, it takes half a day to finish, so not so instantaneous. So you see here the various output files that is created. So all the output files starts with the free letter that we choose, that was 100, and important free files are these X1 RMC, which are the GNXAS signal and the fitted one. So I will try to plot it. I think second column is experiment and third column is the fit. And if I remember correctly, the fifth column is the residual, which is the difference. Of course, you can open the file and there is it's written there what each column is. I will show you later. Yes, okay. So as you can see, the red one is the experimental data that we input. The green one is the fit by the RMC, and the blue one is the residual. So it's the difference between the two.
Fabi, you're talking about a plot?
Yeah.
So I don't see any plot actually.
Really?
No.
Yeah, unfortunately, it seems that we see only.
On your
We don't
screen?
see the graph. We see only the text. There is no transport of the graphical window for some reason.
Wait. I think maybe. Wait. Maybe when I shared my screen, I shared only the terminal. Yeah. Now you can see it? Yeah, okay. Sorry about it. Okay.
It's a very good fit.
Yeah. Okay. So this is for the GNXAS, and then there are other output files. So let me show you first this GNXAS file, what it contains. So what each column represents is written here. So first one is energy, or K, depending on what you have on your input file. Then you have the experimental signal, the theoretical one, calculating on the last configuration, and then the average one, calculating on the the last configuration after equilibration, that parameter that we put in the input. And then we have the residual and the noise, and last one, the noise estimated by the program.
Fabio, what exactly is the difference between the third and the fourth column? Because second is the experimental intensity, if I understand correctly. So third is the Because the fourth column you told it's the average, it's the final configuration of the theoretical intensity.
So, yeah, so the third column is the signal calculated from the last configuration of the RMC. Instead, only last. Yeah.
Okay. So now,
Instead, this one is the average starting from the equilibration point. So,
okay.
yeah, if you remember in the input,
Yeah, I understood the point. Yes, okay.
there was this parameter.
So is it also possible to extract the intensities at different configuration point to see how the intensity is evolving? Like for example, right now you have the third column as the last accepted configuration.
Yeah.
So if you have 100 configurations as a function of configuration to see how the intensity is evolving, or stepwise, it will be a lot of data, I believe, but
yeah,
in principle, yes.
In principle, yes, but right now you have to do it, let's say, manually, because you have to stop the simulation at a given point and then restart. But yeah, in principle, it can be done. So yeah, the average one was how to say, starting from this step. Yeah.
I think if you change from n storage to 50 to 1, you store each position in the final.
Yeah. So also, it's a possibility. Yeah.
Okay. Just.
So in that case, we will have totally about 150 configurations individually stored.
Yeah.
Yeah, but
then of course you need to recalculate anyway.
Yeah. Yeah, but everything is possible, but of course we have to make a choice. Otherwise, it's too heavy. Maybe another comment, but probably Fabio did it. All the parameters that Fabio mentioned were also based on. I see that. For example, we have E0, which is 0 because I think it's a k-scale, it's a wave vector scale in this case, and the S0 square. All are taken from a final fitting, done with GNXAS. So they're not coming in a random way, but should be, and also the experimental resolution, comes from that. So there are numbers that, and you can find more information probably on the documentation if you really want to know more details. And I thank Fabio for his efforts for this.
Thank
you, Fabio.
Yeah. As Andrea said, if you want to really know everything, usually when we did the school, it took 1 week. So in 1 day, it's difficult to.
Yeah. So yeah, I agree with that, because if somebody really, if I would like to know the step-by-step things and then really evaluate everything, yes, it is going to need time. I just want
sure. Yeah. So, but the manual is quite detailed for that purposes. So. Okay. Anyway, so the other output files. So as I said, is the radial distribution function. So again, if you look at this rad RMC file, you basically have first column is r, the distance, and then you have this radial distribution function as a function of r. And again, you have from the last configuration and averaged one after equilibration. So we can try to plot this also. And of course, in this case, it's 2 atoms molecule. So what we have is only a single peak, basically. And I will plot the second and the third column just to show you the difference between the last configuration and the average. A moment it takes from coming from Hungary.
No, it's Czech Republic.
Czech Republic, sorry. Okay, maybe can do it. Okay, so yeah, I wanted to zoom, but maybe better to do it by
Set the scale to.
yeah, better to do it manually, because I think with the mouse it's a bit. Yeah, okay. So this is the peak. So as you can see now, we used only 100 replicas, and also we used quite, how to say, large step in delta R. So we have this very, how to say, squared-like peak. And so red one is from the last configuration, and the green one is the average one. So you can see, okay, maybe here it's difficult to see, but usually the average serves also to smooth out the pair distribution function, because usually one configuration is not sufficient to have enough statistics to have a smooth radial distribution function, but you could have some noise-like feature. And of course, if you increase the number of atoms, you can also use a more finer mesh for the distances, so that you can have more, how to say, an accurate description of the peaks. Okay. Then last file that I will talk about is this run RMC, and this contains just various parameters of the RMC simulation. So like the steps, the number of atom moves, the residual, and it's the ratio of accepted moves. So we see, like, in the beginning, very only 20% of moves is accepted, and then the delta step is diminished. So the delta step is the last column. So is exchange, and okay, this you can see it. Then there are also output files for top drawer. If you are interested, maybe you can see on your laptop by doing again TD PA100, for example, and these show you. If I remember correctly, now I cannot show you from here because it's too slow to load, but it will show you the initial EXAF signal and the last step EXAF signal. So you can see how it changed from the initial configuration to the last configuration. So maybe this could be interested regarding the previous question. So then of course you have the file of the coordinates, and this you can use it for running whatever kind of statistical analysis you want to do on your system. So okay, maybe I can open it. So this is the same file as before. So if we look for RMC, you will see that now it appended other configuration after the final one. So this is after 50 step and after 100 step, because we decided to save a configuration every 50 step. So for example, if we want to continue from this final configuration, we have this start here. So in order to start from this point, we should remove the previous one. So this is the initial one. So if we remove this, then the next simulation that we run, we start from this configuration. So we can continue minimize or doing additional calculation to improve the statistics. Okay. And yeah, for RMC, it's finished. So maybe now we can briefly see another GNXAS example. So we can see germanium. So since before we have seen a molecule, we'll see a crystal case, also to answer some of the questions that were done before. So if you go into the germanium folder, which is called GA, and you go into the CRIMOL folder called the CRI, we can open the CRIMOL input file. Which is this C bar G underscore CRI CRI.in. So if we open this, so in this case, it uses this symmetry flag to describe the structure. This symmetry probably is the quite complicated way to explain, but basically you give the unit cell and you give the symmetry vectors. Maybe Andrea can explain better this point, but another way for describing crystal is instead using CRI. But in that case, you have to give the how to say, all the numbers in your unit cell. Instead of using sim, you need only one atom, and you can give all the symmetry variations.
In any case, I suggest for this very standard, crystal holographic problems, I suggest to read the handbook, the red book, and for the details, because are rather standard. Yeah.
Yeah. So I will go. I will show you here. So, but yeah, as Andrea said, it's quite standard. So you will give either, if you choose symmetry or crystal, then you will give what type of unit cell you have. So if you have a triclinic, cubic, hexagonal, etc. Then depending of what unit cell you have, you need to give some parameters. So of course, like for cubic, you only need one lattice parameter. For hexagonal, you need two. For other system, you need all three, ABC. And then you, for some, you need to give also the angles, while for some unit cells, the angles are defined. So this is, the usual crystal configurations. So in this case, for germanium, it's cubic, so you only give one parameter, and then this is actually a symmetric operation. Okay, here it's written in more details what these numbers means. These are translational symmetries. Yeah, components of the translation in fractional units. And then this last one, additional possible translation written in this form. Maybe I can show you on my laptop another example just to be more clear. But another point is that, as I said before, in the case of molecules, we had the real distances in angstrom, while for the crystal system, we use the fractional coordinates. So let me look for maybe I can show. For example, I will show you the input file for copper oxide. Okay, hopefully you can see.
Yeah.
And so in this case, it's cuprous oxide, not copper oxide. So C2O. So in this case also it's in this case I use this crystal flake, and this is a cubic system with the lattice parameter 4.2, and then you have to give all the atoms in the unit cell. So in this case, there are 6 atoms, and you have to give the position for the copper and the oxides as a fractional coordinates. So this is just to show you for a crystal case. Then the rest is the same. After you run Kreml, you have the input for Fagen, and you can run GMP. Let me close this. So we'll go back to this germanium case. So we can see the Gmp output files. So in this case, we will have the various two-body distribution peaks. So we have the first shell for atoms, because germanium is a diamond configuration. So the first peak, the second shell, the third shell, and so on. And then you have the free body distributions. So you have this first peak between the two nearest neighbors and 109 degrees, which is the angle of the diamond configuration, and so on. So then, of course, you can calculate all this and then use it to fit it. I will show you on my PC. So and you can do just to show you the fitting in this case for the crystal. So at 80 Kelvin, so hopefully you can see. So this is the plot with top drawer. You can do it also on your cluster. So I did it from my PC, but if you do TD PX in sorry, I will show you the folder. So the folder is this GA fit. I choose 80 Kelvin, but you can see also for room temperature and amorphous germanium. And but what you see is that in this case we have many more multiple scattering signal that are required to fit the experimental data. Actually, you can see that if you look at the residual, there are still some additional oscillations, so maybe even more signals are required for a proper fitting. If we look at the room temperature one, this already it's better fitting. So with the same number of multiple scattering signals. Okay. So the process is the same that we have seen earlier for the CCl4 case. Just what it changes that in the Kreml initial configuration we have, as I said, the unit cell with the fractional coordinates, and then for the end body distribution we will have many more peaks, and you should decide how many you want to use for your experimental data. So I think, yeah, I leave the time for questions, and then, I mean, we can conclude.
Okay, so then let us first and foremost let's thank the speaker Fabio, who spent almost the entire day teaching us how to use GNXAS. I mean, and also Andrea, who gave us the physics basics in the morning for the talk. I mean, for hands-on session. So now it's open for questions. Any questions? Okay, so well, whatever questions I had, I was asking when I was following.
Okay, yeah. Thank you.
So any other particular questions? But if not, it's let us ask our online participants if they have any particular questions or anything that needs to be answered. Please write it up in the discussion. Or also it's okay, so because you can contact Fabio if it is okay. I mean, you can send the email and ask while practicing. Anyway, you get into some problems here and there, so you can contact Fabio if it is.
Yeah, and I remember the GNXAS website. Actually, maybe I can show you.
Yeah.
So, which is gnxas.unicam.it. So this is the website, and if you click here on GNXAS, you can find the information.
I see. Okay.
Okay.
No, tomorrow. Okay, so just I want to also to thank you, the two of you, and especially Fabio, who spent part of the night working. Because what time is it now, Fabio?
It's midnight. Okay.
Half past
Not
midnight.
great.
So have a good night, and thanks again.
Yeah, thank you. Thank you. Thank you, and thanks all the work that has been done by the organization, also by the cluster and the Zoom support in the last hour. Just been great. So thank you.
Okay, so then thanks all. So let us close the session for today then, in that case. But so we can. There seems to be something in the discussion. Okay, so. Okay, then so. So I think yes, we are done for the day. So let us finish. Okay, and once again, thanks Fabio for taking this time out and then patiently teaching us step by step everything. Okay.
Thank you.
Okay then, see you.
Okay, see you. Bye everyone.